on decision trees. So before we get into actual decision trees, let's first clarify what is the difference between a classification problem versus a regression problem. So classification is when you're trying to distinguish different entities into different groups. For example, one classification task may be given photos of fruits, determine um, determine what type of fruit is in a certain photo, right? So that is a classification task because you're trying to distinguish the different photos into different groups according to what fruit is in the photo. Regression is a bit different in that you're trying to predict a numerical output that is like um, for example, predicting house prices given some house features, right? So given the number of bedrooms, number of bathrooms, the amount of land outside the house, predict the price of the house, right? So there, you're not trying to determine what group this some entity falls into. You're trying to predict a continuous numerical output um, given some data about the house. And so these are two different machine learning tasks, and we will cover algorithms that are able to solve both. Decision trees specifically can actually be used for both, but we will mostly be focusing on their use for classification, not regression. In future lectures, we may also go into regression. Another thing to clarify before we get into the specifics of decision trees is what are features in machine learning versus labels. Um, So in machine learning, we're trying to predict something about some data, right? And this data can be from anywhere. In this image that you see here, each row of this table corresponds to some patient, some medical patient, and these three columns, all four of these columns actually corresponds to some data about this patient. So this column corresponds to whether or not the patient smokes. This column corresponds to whether or not the patient consumes alcohol. This column corresponds to whether or not they engage in some sort of physical activity a certain number of times a week. And then this represents whether or not they have some cardiovascular disease, right? And so in this specific machine learning task, the goal was to train a machine learning model that inputs all of this data. So we see whether or not the patient smokes, consumes alcohol, and is active. And we have to make this machine learning model able to predict whether or not they have a cardiovascular disease. So if you think about it, if you think about the machine learning model in terms of a mathematical function, you can think of, if you have like your standard f of x equals y notation, um, all of the stuff in this blue box are like the x, right? These are the things that you would input into the machine learning model. And then all of the stuff, this column in the red is like the y. This is what you would expect the function to output. So in machine learning, we usually call the input things features, and the outputs or the y labels. And so this is just a bit of terminology that we'll be using throughout the year that you should be acquainted with. So hopefully that made sense. Talking about the difference between training and testing data sets. So in machine learning models, the goal is to feed in the training data set so the machine learning model learns the relationship between the data, and then we predict some information using the testing data, right? So this is basically the same screenshot from the previous slide where the first three columns, whether or not we're smoking, whether or not we're drinking alcohol, and whether or not we're active, are the features, right? And then the cardio column is the labels, or sort of the answer, what we're trying to predict. And so the training data has both the features and the labels. And we want to feed all this data into some machine learning model where these are like the inputs and these are the outputs, and then teach the model the relationship between these x's or these inputs and the y's or the outputs, right? And so once the machine learning model has successfully learned the relationship, or as well as it can, learn the relationship between these variables, we want to be able to predict the information given only the inputs, right? So this testing data only has the features. It only has whether or not we're smoking, whether or not we're drinking alcohol, and whether or not we're active. And then we need to predict the cardio column, right? This is basically the difference between training and testing data sets. So now getting into the specifics about decision trees. So what is a decision tree? A decision tree is just a collection of different questions that we can ask, and those questions, when we ask them about a certain entity, it produces some useful information. For example, this is an example decision tree that may happen in your life. You know, given a certain day, which would be like our entity, do we have work to do? Either yes, stay in, no. This is basically a decision making process to decide what you do at a certain time, right? The decision tree models that we'll be working with um, are going to be used for classification, at least in this lecture. And the key part about making a decision tree is asking the right questions, right? The questions are what make up the decision tree. And so, in order to create a decision tree that does something useful, you have to be able to determine what are the best questions to ask at every node in this tree. So the first concept that we're going to be discussing is Gini impurity. And Gini impurity is a way to measure how impure or how pure some collection of data is. And you'll see what I mean by pure and impure on the next few slides. But just before I go into those, just to explain some of this notation. So this is called sigma notation. If you haven't seen it before, it's like basically a for loop where you're adding something every time, right? It's a way to sum over some quantities. It's a basically a notation to represent like some condensed addition, right? It's a shorthand way of representing repeated addition. So this whole statement basically says, so the impurity, the Gini impurity, that's why there's a G here, the Gini impurity of some data I is equal to 1 minus the sum for each class in the data, the probability that a randomly selected item from the data corresponds to that class. And all of the probabilities are squared. We'll go into like examples to make sure you understand this, so don't worry if you didn't get all of it. But remember, if you keep, make sure you know what each of these letters mean. K here is just like a index variable. It keeps track of which class we are on, and C is the total number of classes total. That is the total number of classes that we have in this data I. And this may not make sense at all, but it will in the next few examples. Okay. So let's go ahead and calculate the Gini impurity for each of these data sets, right? So this is one data set, this is another data set, and this is another data set. And we're just going to apply this formula here and then see what the Gini impurities are for each of these groups of marbles, let's say. So take a minute, try to do it on your own, right? Here, K is, as I mentioned before, the index variable, and C is the number of classes. Here, there are two classes, right? There are two types of objects in our data set. There are blue balls, or blue marbles, and then there are red marbles, right? So, what's the probability that you pick a blue ball? It's 1/2. And what's the probability that you pick a red ball? It's also 1/2. So given all that information, try to calculate the Gini impurity for this data set. Pause the video. So if you did this, let's do this sort of iterative method here. You would get 1 minus, and first let's do it for the blue balls. So the probability that you pick a blue ball from this from this data set is 3, 6. And so we square that. And since this subtraction sign is here, we actually have to subtract each of these probabilities away from 1. Even though I said this is addition, if you think about the distributive property, this minus sign will distribute over to each of these different elements, and so that's why we have a minus sign here and here. But hopefully it makes sense that this is 3, 6, and we square it, and then the same thing for the red balls, right? Because the probability that we pick a red ball is also 3, 6. So once we have this, we calculate 1 minus 3, 6 squared minus 3, 6 squared, and then we would get 1/2. So in terms of impurity, and this is actually the most impure you can have, right? If you think about the opposite, what would be the most pure data set? The most pure data set would be all of the balls one color, right? This is the exact opposite of that. We are completely mixed, and so this is the most impure data that we could possibly have. Okay, now let's do it for this one. So it's the same procedure as before. First, let's go ahead and do it on your own, and I'll explain. So hopefully you got this answer. Basically, what you do is first, I did the blue balls. So you find the probability that if you randomly select a ball, it will be a blue ball, and that is 2, 6. And then you square that and subtract that from 1, and you do the same thing for red balls, which is 4, 6, right? And once you do this, you get 4 9s, which is equal to 0.444. So if you think about this in terms of purity and impurity, you can see that this is sort of this is more pure than the previous example, right? Because it's getting closer to the purest form, which is all of them one color, right? If you think about all the balls being red, and that being the most pure, this is kind of taking one step closer towards that state, right? Because there's one less blue ball, which means we are supposed to be um, less impure or more pure. And if you remember the value from before, which was 1/2, this value is 0.444. This actually repeats, but I didn't include all of them, obviously. So this is going to be less pure, less impure or more pure, right? So Gini impurity is a measure of the impurity, where the higher the impurity, the higher the number. And finally, let's calculate the Gini impurity for this data set. As you can see, there's only one class, so hopefully you already go ahead and try. So hopefully you got this answer, where since there's only one class, the probability that you pick a red ball is 6 out of 6, and so that's just 1, and then when you subtract that, it's 0. So just listing out all of the impurities here, the Gini impurities. Here you had 0.5. This was the most impure we got, or the lowest purity. This one was a little more pure or a little less impure, and this was the most pure or the least impure. And so just to note, 0.5 is actually the maximum possible impurity, and 0 is actually the minimum possible impurity. You can't get higher or lower than these two extremes when you're calculating Gini impurity. And just note that Gini impurity can also be extended to problems where there are more than one class, right? In these examples, we only had blue and red balls, but this could just as easily been applied to, whatever the number of classes are. If C was like 3 or 1,000 or whatever, the same formula can be applied. And so now let's talk about information gain. So information gain is basically the criteria that we use to select what question we should ask at a certain node when creating our decision tree, right? So if you remember, decision tree is just a series of questions, And so we want to figure out what are the best questions to ask that make our resulting data most pure. I'll get into exactly what that means on the future slides, but this is the formula for information gain. Just to go over some of the variables here, dp, d left, and d right are the data sets of the parent node, the left node, and the right node, right? So these are like the data that is contained in each of these nodes. This function I here is a measure of impurity. There are actually several measures of impurity, but the one that we're covering in this video is Gini impurity. NP, N left, and N right are the number of items in the parent left and right nodes respectively. And F right here, which is you don't see anywhere here, but is actually used to generate DP, D left, and D right. F is the question that you are currently considering that you calculate information gain for. And so when you're creating a decision tree, you basically come up with all the possible questions that you can ask, generate the resulting left and right nodes for that question, and calculate the information gain. And then once you do that, you find the question that resulted in the most information gain. And that is the question that is the best question to ask. I'll get into exactly what that means on the future slides. So let's say that we have a task where we're trying to categorize different athletes given some features about them, right? So let's figure out, given some characteristics, whether a athlete is a tennis player or a basketball player. And so this is only a one level decision tree, right? So in reality, most decision trees are several. Their depth is much larger. You can keep asking questions. So once you differentiate these once you get this set, you treat this as a parent node and then ask a different question, and you keep going. Here, this is only like depth of 1, and we're only considering one question, but this is just an illustrative example. In practice, just remember that decision trees can be arbitrary depth. There's no limit here. And so in this example, we have two questions that we're trying to consider. So here, the question that we're asking about each of these players is whether or not their age is greater than 27, right? And so on the left side, you have all the players where their age is not greater than 27, so they're younger than 27. And here, you have all the players who are actually older than 27. Here, on this is the same parent node, but we're asking a different question here, and as a result of that, the left and right child nodes, or like the nodes that come out of this parent node, they're a bit different, right? Because we're asking a different question. Here, we're asking, is the height of each of these players greater than 6 foot 4 inches? Here it's no, and here it's yes, right? So when we're judging or not how good a question is, just looking at this, we can kind of see that this is the better question, right? At least here, we kind of have the most pure possible thing where we have two tennis players and no basketball players. And here we're very close to being perfectly pure, except for this one tennis player, but we almost perfectly classify or differentiate the players into different categories, like tennis player, basketball player, right? Whereas here it's a bit more split, and it's not that clear that this question actually led to some, like, this question, it's not clear that this is as good of a question, right? Because the athletes are not as well differentiated. But we kind of eyeballed that. So information gain is a way to like mathematically calculate which question is better to ask. And so we're going to walk through that here. And just note that this is kind of like arbitrary. I don't actually know if these patterns are true. I mean, I think basketball players are taller than tennis players on average. But I'm not sure about this. I kind of just made it up. So don't take that like seriously or anything. Yeah. So this is the first. This was on the left-hand side of the last slide. So let's calculate the information gain here. So we want to calculate first. The first thing that we want to do is well, in code, the first thing you would actually do is split up this group into the left and right children nodes, right? So you get this and this. But since we already have that on the slide, the next thing to do is calculate the impurity of each of these groups. Since we already did impurity and we covered that, I'm not going to walk through the individual steps, but take a minute. It's always good to practice, and then calculate the impurities, and then I'll have the answers on the next slide. So go ahead. So hopefully you got these values, right? These are both the same because there's one of one class and two of the other class. Here there's actually it's a 50-50 split, and we kind of already did that previously. So and that was 1/2. So we have all of these items now. We have IDP, ID left, and ID right, where IDP is 1/2, ID left is 4/9, and ID right is 4/9 as well. And so now the only thing we have left to do is actually plug in the n values, and the n values, if you recall, are just the number of um, entities that are in the left node, the number of entities that are in the right node, and the number of entities that are in the parent node. So you can find those just by counting. And so go ahead, do that, and then plug in all those values in here, and then get the information gain. So hopefully you carried out these calculations, right? So 1/2 is just IDP, and then 3/6 is the number of it's n left over np, where n left is 3, right? There's 1, 2, 3 elements here, and then np is 6, and same thing for this side as well. And so that results in a fraction 1/18, which gets you 0.0555 repeating. So now let's do the same thing for the right hand side. Again, we're following the same procedure. Let's first calculate the the Gini impurity for each of these nodes. I think I may have misspoke. I'm not sure, but I think I may have misspoke on the other slide when I said this is information gain. This is impurity. So, if I made that mistake, I'm sorry. So go ahead and calculate the Gini impurity for this. We already did this, right? So this side and this side. So go ahead and do that. So this again was 1/2. This is actually 0. It's perfectly pure. And this is 3/8. And so now we can just follow this formula again, and then plug everything in, and then so go ahead and do that. And so the information gain here was actually 0.25. Right? Hopefully all of these make sense. 0 here because there's a 0, 2, 6 because there's 2, and the number of nodes in the number of entities in the parent were 6, and so on. So here the information gain was 0.055, repeating, and here it was 0.25. And so since the information gain was higher for this this question here that we ask, whether or not the height is greater than 6'4", this is a better question to ask for the purposes of differentiating whether or not a certain athlete is a basketball player or a tennis player, right? And so, we kind of knew that already just by looking at it, but this is, hopefully it should make sense that this is like a mathematical way to carry out the same process and determine whether or not which question is better. So one thing that you may be wondering is how to come up with these values, right? So when we said age is greater than 27, how do we know why can't this be like age is greater than 3 or age is greater than 59 or whatever? Usually, the most straightforward way to do this is to just iterate over all the elements in your training set and then try out different questions, like different values based on the actual features of your training entities, right? So if one of these basketball players, let's say this is your training set, and one of these basketball players has a height of 6'1", has an age of, let's say, 28, you try out 28. And let's say another one of the basketball players has an age of, 23, so you try out 23. And let's say, so for not just basketball players, but also the tennis players, you try out all their ages here, and then find out which value is the best to ask. And it's not just you don't just do this for the values. Actually, you also do the same iterative process for the actual feature that you're using, right? So on the previous slides, we were wondering whether or not age is greater than 27. Is that a better question, or is height greater than 6'4" a better question? But in usually when we have this, we would try out every single, like, let's say we have the characteristics age and height, and then we have different values for age and height for each of these different players. So we would try out all of these questions, um, like we would try out age is greater than, and here we would replace it with like 6 different values for each of the 6 ages of the people here. And then we would try out, here, um, is height greater than, and then 6 different values for all of the 6 different heights of these players, and put it here. And so that would be a total of like 12 different questions. You calculate the information gain for all of those different questions and then choose the best one. So hopefully that made sense. And if we have more features to ask, here we just are asking age and height, but let's say we had a different question like number of injuries in their career. I don't know if that's like a good feature to include, but let's just say that we did that, and each of these players had a different value for that feature, number of injuries. Then we would have 6 plus 6 plus 6, which is 18 different questions to ask. So hopefully that made sense. That's how you come up with these different questions. So one problem that may come up when you're creating your decision tree is overfitting. And overfitting is basically when you almost memorize your training data and you're not able to generalize well to your testing data. And so this can be visualized in this graph over here, where the black line is like the optimal model that we would like to have, right? It pretty cleanly separates all the blue dots from the red dots, with some exceptions, like this dot here, or this dot here, or this dot here. But those seem like kind of outliers, right? It's not, those seem kind of like weird exceptions. Overfitting is what happens when we have a green line here that separates the data almost like perfectly, but it's clear that this kind of is going against the pattern that we have, right? The clear pattern here, the most obvious thing, is that this smooth line is separating the blue and red lines, but when we have this sort of like jagged model that is trying like very hard to separate it, all the dots perfectly, that's what we have. That's what we call overfitting, and this kind of reduces the ability to generalize to different data sets, right? Because we're almost memorizing our training data set, but in theory, you would predict that if we had more data that we were going to predict on, for example, any blue dots that fell here or here would be misclassified, right? Um, so because we are memorizing the training data, we are going to be performing more, we're going to be performing worse on the testing data. And that's something that we don't want. So overfitting is a problem in like all forms of machine learning, right? It occurs when the model is too complex and basically memorizes the training data. So for the specific example of decision trees, there are 2 main ways you can prevent overfitting. One is to only continue to generate, different, only keep asking questions until the information gain is keep asking questions if the information gain is larger than some threshold. And if no question that you can possibly ask has an information gain greater than that threshold, then just stop, right? So if at a certain point all the questions that you're asking are not doing that well in differentiating the different items in a certain node, just stop asking questions. Another thing you can do to prevent overfitting is to prune all the nodes that are greater than a certain depth, right? So if you recall, in the previous examples, we had a depth of 1, right? But you can imagine that for each of those child nodes acts as a parent node, and each of those child nodes has more child nodes, and so you could keep going down and down levels into lower and lower depths, or higher and higher depths. And then pruning is basically cutting off all or deleting all the nodes that are after a certain depth, right? And so that basically prevents you from asking questions that are super specific to your training data set, but don't generalize well to your testing data set. And so that's basically it. Hopefully you learned something from this lecture. Next time we'll be talking about random forests, which are an ensemble machine learning algorithm that is basically a collection of decision trees, and we'll also be giving more information about how to code up decision trees. We'll have a lecture that goes into that. So thank you, and hope you have a good day.